Dear friends, welcome to a video introducing the resistivity method as a geophysical surveying technique that is predominantly used for the near subsurface, meaning typically a few tens of meters in depth. And this zone, which is sometimes also referred to as the critical zone, typically encompasses things such as the topsoil, the transitions of unsaturated and saturated depth intervals that go along with an aquifer if present, and it also contains a transition between weathered and unweathered bedrock material. An example of this method is shown here from our very own applied exercises of this course, where we investigate the critical zone in a valley with much fluvial sediments and an aquifer that starts at a few meters beneath the surface. Other applications of this technique include, for example, the localization of waste disposal sites, the detection of contaminant plumes, and many other scientifically meaningful applications. The way the resistivity method operates is that it characterizes the subsurface as a function of its ability to conduct direct, as opposed to alternating, electrical currents. A material that has a high electrical resistivity will conduct electrical currents poorly and vice versa. And as we will see in a little bit, the resistivity method is an active method because an active source in form of a battery is required, and this sets the resistivity method apart from passive methods such as the gravity or the magnetic method, where no such active source is needed. The learning goals of this video are first, that you understand the very basic principles of how the resistivity operates. And second, you should be able to derive flow patterns of electrical currents in the subsurface, and this is where we will use a number of equations. And third, you should understand why we need a survey layout that includes 4-point measurements and what the concept of the so-called apparent resistivity is that goes along with that. So let's first define the geophysical parameter of interest, which is the resistivity, meaning the ability of a material to conduct electrical currents. And in order to do this, we need to consider Ohm's law. And Ohm's law states that an electrical current I, which corresponds to the amount of moved charges per second through a wire, for example, that current is linearly related to a potential difference, delta U. And the constant of proportionality is the resistance, capital R, with the units ohms. If you have ever connected a battery to a light bulb, you are familiar with this, as the battery provides the source for the electrical potential, the current flows through the wires, and the bulb has a given resistance controlling the electrical current and hopefully preventing a shortcut. The overall resistance of such an electrical circuit, however, also depends on the geometry and the type of the cables that you use. If the cable has a smaller cross-section A, it will conduct the electrical currents less well. And also, if the cable is longer, the overall resistance will be higher. Last but not least, some materials conduct currents better than others. For example, copper is a very good conductor and silicon is not. And this clarifies that the electrical resistance, capital R, depends both on the material properties and on the material geometry. And this marks the important difference between resistance and resistivity. In German Widerstand und spezifischer Widerstand. The resistivity, ρ, with units ohms times meters, is purely a material property, and this is what we are after in geophysics, and hence the name of the method. The conductance and conductivity, in German Leitfähigkeit und spezifische Leitfähigkeit, are defined completely equivalent in the sense that the conductance is the inverse of the resistance, and the conductivity with units Siemens is the inverse of the resistivity. There are different mechanisms of how currents can be conducted, and the two most important ones are metallic and ionic conduction. Metallic conduction is what happens, for instance, in a copper wire, where electrons are delocalized in the so-called conduction band. But in our case, more important is the ionic conduction, which means that, for example, dissolved ions in liquids are responsible for the charge transport. And this would be a dominant process, for instance, in a saturated aquifer or also in unsaturated soils. In general, the ways currents are conducted in materials that are relevant for geo and environmental sciences can be quite complicated. And the theory of Archie's law is one avenue to go into this in more detail. However, for now, we just appreciate the wide range that the resistivity covers. For example, the difference between salt water and rainwater alone is easily 3 orders of magnitude. And this is because salt water contains much more dissolved ions. Groundwater, where, let's say, the geometry of the pore space is also important, equally covers a quite impressive range, which is, however, still distinctly different from various rock types, which are all comparatively poor conductors. And this immense spread of the conductivity/resistivity is a curse and a blessing at the same time. On the one hand, the resistivity within the critical zone can have a comparatively high contrast, given that the availability of water changes significantly with depth. But on the other hand, it will be difficult to assign any given resistivity value to a specific material alone. The principle of the resistivity method can be compared to the simplest electrical circuit, which contains a battery as a source for an electrical potential. It contains electrodes, meaning essentially metal sticks where we inject the current into the subsurface. And then the electrical circle is closed with cables, which in our case corresponds to some yet to be determined flow path of the electrical current through the soil. And this soil has an electrical resistance, which in our case will be a combination of the material properties, meaning the resistivity, and also the geometry, meaning the distance between the electrodes located at the surface. And ideally, we would like to probe how this resistivity and the resistance changes with depth, so that we can assign different material properties accordingly. The big difference is that we obviously don't have any cables in the subsurface, but instead we expect for any given electrode spacing that the electrical current somehow flows distributed through the subsurface. And in order to understand how the resistivity method works, we need to predict the shape of these flow patterns, and this in turn requires a vector version of Ohm's law. This vector version of Ohm's law is formulated in terms of the electrical current density J, and this density is defined as current per unit area, and it also contains the electrical field E. Both quantities, J and E, are vector fields, meaning they are defined everywhere in space with a direction and a magnitude. In the cases we consider here, the current density J is always parallel to the electrical field, and the constant of proportionality is the conductivity, or its inverse, the resistivity. In the exercises, you will show that this is a more general formulation of the Ohm's law U equals Ri that we used in the previous slides. So once we accept it, we can directly define the scalar potential field U that has units volts, and we do it in the exact same way as done for the potential field in the gravity method. The scalar field U defines the amount of work required to move a charge along a given path in the electrical field E. This means we can calculate U from E by evaluating a line integral, or vice versa, we can derive the electrical field from the potential field by calculating the gradient. And those are the equations we need to predict the flow patterns in the subsurface, and we do it for the simplest possible case, which is a homogeneous half space, which means that the conductivity and resistivity in the subsurface are constant everywhere. Above the surface, the conductivity is 0 and the resistivity is infinite, so please no electrical currents up here. And we solve this problem in steps by first considering a homogeneous half space with only one electrode, and the other electrode is so far away that it doesn't really matter anymore. Now the task is to derive the current flow lines for this system, so let's go. We have a surface and one electrode. The amount of current I that enters the subsurface at this point is known and we can control it. So what else do we know? Well, Ohm's law is valid. And instead of the electrical field, we can use the gradient of the yet unknown electrical potential U. The electrical field vectors will be oriented perpendicular to the equipotential lines of U. Remember, it is often easier to calculate the potential U first and then derive the electrical field, and an example where we did this was when we derived the magnetic dipole field. However, this in itself is not enough information to solve the problem. We need additional physics here, and this can be done. We know that at any point in the subsurface, other than right at the electrode, the current flow density J must be conserved. What does that mean? It means that if we define a box away from the current electrode, then the amount of current flowing into the box and out of the box must be the same, because there are no other sources or sinks which would create or destroy electrical currents in our domain. And thanks to our analysis of the magnetic field, we know how to formulate this mathematically. It means that the divergence of J is 0 everywhere, apart from the position of the electrode. Here I formulated the divergence in Cartesian coordinates, and remember, in other coordinate systems, such as spherical coordinates, this may look very different, but the geophysical interpretation obviously remains the same. So using this conservation law, we finally arrive at the governing equation, which is the Laplace equation. And this Nabla operator squared is called the Laplace operator, and in essence it contains the sum of the second derivatives, and down here I spelled this out for Cartesian coordinates. So this equation is a second order partial differential equation, and those are generally very difficult to solve. For starters, many scalar fields U will satisfy the condition that the sum of the second derivatives is 0. For example, any constant or any linear field will do that. So again, we need additional information to single out the correct solution, and we do this by formulating the correct boundary conditions. There are two very reasonable conditions. First, far away from the source, the electrical potential should be negligible. I am sure that right at this instance, somebody is doing a resistivity survey somewhere around the world, and I surely don't notice this in this very room. Second, please no currents above the surface, which would not be good for the person doing the survey, and therefore the component normal to the surface of J must be 0. Air is a good insulator, so the current should not shoot out of the surface, but we have no problem if it flows parallel to it. With those two conditions, we can solve this differential equation using a technique called separation of variables, and we will show you in the exercises how this can be done. Here I just present you the solution in spherical coordinates, and it is a somewhat simple solution which is also familiar to us. The electrical potential U, written here in spherical coordinates, decays with 1 over r. R is the distance away from the electrode, and A is an integration constant that needs to be determined yet. First, let's visualize this. And here I show you some code snippets of how this can be done. Mesh grid in MATLAB or Python or any other language takes care that this field is defined everywhere in space. And here I have a vertical slice of this three-dimensional field, and I choose to visualize it with equipotential lines, which are also referred to as contours. Okay? And this is easy enough, and the result is really not overly spectacular. Everything has a nicely spherical symmetry, and using Ohm's law, we can now visualize the streamlines through calculating the gradient. In this example here, I take the gradient along the x and the z directions only because I visualize a vertical slice. However, we really don't need any computer code here at all, because we know that the field lines are oriented perpendicular to the equipotential lines, and so clearly this will look like this graph here with flow lines flowing in the radial direction outwards. So what remains to be done is to determine the yet unknown constant A, and here we do it using, again, sort of conservation principles, okay? So per definition, we know that the current I is the current density J times the area of the half sphere in the subsurface, which is given by 2πr squared. So we can replace the current density as done before with the gradient of the electrical potential U, which we now know. So it is A over R, and taking the derivative of this with respect to R gives us 1 over R squared, which cancels this R squared over here. And so we end up with this equation. Note that in this last step, I replaced the conductivity with its inverse, the resistivity, which is the more often used notation here. So now everything is solved. We know the potential U, we know the current I, and we can rearrange this equation for the unknown resistivity. And after all this detour, we arrive at an expression which is essentially Ohm's law again, but now formulated in terms of the resistivity and not the resistance. All of this work was not in vain, because remember, this is only an intermediate step. It is only valid if the second electrode is very far away. So now we relax this assumption and consider a half space where the second electrode is relatively close. So the picture now looks like this. We have a positive and a negative electrode where the current enters and exits the surface respectively. And we now need to determine the potential at any given point P1 as a function of the two distances R1 and R2 from the two electrodes respectively. Now the solutions from the previous step come in very handy. The potential at P1 due to the electrode 1 is given by the solution from the previous step, and the potential at P1 due to the second electrode can be described in the same way, but with a negative sign to account for the different polarity. So the joint effect will be the superposition of the two contributions, and this type of expression is familiar to us. It strongly resembles the potential of a magnetic dipole that we derived previously. Unfortunately, we cannot use the far-field approximation next, because the field between the two electrodes at small distances is very much of interest here. So maybe instead of using a far-field approximation, we first go ahead and visualize the shape of this potential with minor modifications of the code snippets that we saw previously. So instead of visualizing the contours of one potential, I do this now for the superposition of two potentials, and both of them are shifted relative to the origin with a constant offset, which I call L/2, and which corresponds to the spacing between the two electrodes. All the rest remains essentially the same, and this is the result, okay? Far away from the other electrode, the equipotential lines are almost radially symmetric, corresponding to the solution of the previous case. But as we get closer, we see significant deviations, in particular this central equipotential line marks the zero contour where both individual potentials cancel essentially for all depths. Fine. Knowing all of this, we can continue with business as usual, using the vectorized version of Ohm's law to calculate the flow lines from the gradient of the potential lines, and this results in the somewhat unsurprising picture that the current flow lines follow a dipole pattern which we already are familiar with from the analysis of the magnetic dipole. Remember that this is only a vertical slice along the central axis, but we will also have currents flowing into and out of the plane, and the next picture shows this from a bird's eye perspective from above, illustrating the three-dimensional nature. So the current flow lines will also extend laterally from our central array. So with those two figures, we have achieved our goal to understand the shape of the distributed current flow in a yet homogeneous subsurface if the subsurface is inhomogeneous, meaning that the resistivity varies spatially. Then we have to solve the same equations again, but it gets considerably more complicated, and in fact too complicated for this introduction. So for the moment we stop and we reiterate that we need to measure the current and the potential drop at the surface in order to infer the resistivity of the subsurface material. However, there are a number of complications, one of them being the way that the electrodes couple with the subsurface. You have to imagine that the electrodes are mostly some sort of metal sticks that we simply push into the surface, and at the contact areas between the metallic electrodes and the surrounding soils, the mechanism of conduction must change from ionic to metallic. Actually, I mean from metallic to ionic. Apologies. And this goes along with a comparatively large contact resistance. Yeah? So quite literally, if we would wiggle on one electrode, this would change the degree of coupling, and with it the contact resistance, RC1. And this resistance is typically much larger than what we would like to detect in the subsurface. So somehow we need to account for this, and the way we do it is that we don't pick up the potential differences at the current electrodes, but we introduce two new electrodes between which we measure the potential drop. So this potential drop is then in theory exclusively a function of the resistance in the subsurface. So there's a naming that goes along with all of those electrodes. So we typically name the current electrodes, the A and the B electrode, and we refer to the electrodes where we measure the potential drop as the M and the N electrodes. In these 4-point array measurements, it is important to keep track of the relative distances, and here I denote those with R1 to R4 respectively. Surely we will also have issues with contact resistances at those two new electrodes M and N, but here it is much less relevant because no current is injected. So the contact resistance is much less important here. And this is the principle of a 4-point array. Now we need to use our general solution of the potential field between the two electrodes and evaluate the differences at the points M and N at the surface. So up here is our general solution, and then this is the evaluation of this potential as a difference between the locations M and N, and this results here in this double differencing. And we call this factor here, which essentially quantifies the geometry of our electrode array at the surface, we call it the configuration factor K, and we now arrive at a similar solution for the resistivity that now accounts for the 4-point measurement setup with the configuration factor K. In an ideal case, meaning in a homogeneous subsurface, the inferred resistivity from the measured potential drop and the measured current will be independent of the specific arrangement of the electrodes at the surface. However, this is only for an idealized case. If we have an inhomogeneous subsurface, which is definitely the default, then the current flow lines will flow differently depending on the location of the electrodes. This means that every time we take a measurement and then change the electrode setup, we will get a different reading for the inferred resistivity. And this introduces the concept of the apparent resistivity. So in an inhomogeneous subsurface, we can only measure apparent resistivities, and those are a function of our array geometry. Okay? And this apparent resistivity is to a certain degree, let's say, diagnostic of the true resistivity in the subsurface. Yeah? So if the apparent resistivity is very, very high, then very likely you have a poor conductor in the subsurface. However, the true resistivity can only be inferred with more rigorous methods, in particular an inversion, and this we will cover in the following videos. But for now, I think it's definitely enough. I will briefly go through our learning goals of this video again. So I hope that you understand now the basic principle of the resistivity method. Yeah? You should be able to at least roughly outline how we would derive the flow pattern of the current flow lines in the subsurface. And you should understand why we always need at least 4 electrodes in order to do those kind of measurements. And you should be at least roughly familiarized with the concept of the apparent resistivity, and we will work with that further in the videos to come. There are many things which we didn't cover, most importantly, probably the most interesting part, which would be an inhomogeneous resistivity, which is definitely the default in the subsurface, but we also don't really know what is the depth of investigation of this method, how can we do sounding or profiling, what's the impact of a possible polarization in the subsurface, and so on and so on. Many more things to explore, and we will do this together in videos, lectures, and exercises to come. Bye-bye.